This is an introduction of electrochemistry. The teaching is split into two parts, where part 1 we look at electrochemical cell, recapping on redox reactions, as well as introducing and learning electrode potentials. The next part will be about electrolytic cells, like electrolysis that's occurring, and some further calculation. The first part will take up about 3 SDL lessons. So what is electrochemistry all about? Certainly, it involves the study of movement of electrons from one chemical species to another. This is a redox reaction. At the same time, we are very interested in the interconversion of electrical and chemical energy. So we are either producing electricity or using electricity to do a chemical reaction. So the big idea is this interconversion. And if we get chemicals to react to produce electricity, there will be electrical chemical cells, and this is what we'll be covering a lot in part 1 for the next 3 SDR lesson. Here we also introduce the idea of it's a spontaneous reaction of this redox reaction. So delta G is less than 0, and then day-to-day example will be the batteries that we use. So here you can also consider that there's some position of equilibrium that's involved, right, when we look at delta G. And then electrolytic cells would be the non-spontaneous reaction, where we use electricity to drive a non-spontaneous redox reaction, such as electrolysis, electroplating, and even charging your handphone batteries or any batteries that you're charging. The main thing I want to drive across here is there are a good interrelation between your delta G, your position of equilibrium or equilibrium discussion, as well as electrochemistry, which we'll cover in depth on what it's about later on. And at the same time, main thing here is that there are redox reactions that are involved. Let's have a quick recap on the oxidation number. So firstly, elements in its elemental form, there will be oxidation number or oxidation state of 0. Secondly, a simple case of ionic compounds with monoatomic ions. So these monoatomic ions will have oxidation number of the charge on the ion. Giving you another example here, for example, like aluminium oxide, there will be +2 for aluminium and -2 for oxygen. Thirdly, there are elements that have the same oxidation number in the compounds. So these are quite clear-cut cases. Group 1 metal, group 2 metal, aluminium, they would have +1, +2, +3 respectively. Fluorine, the most electronegative element in the periodic table, there will be a -1. Whereas for oxygen, it is usually -2 with some exception, such as in peroxides, H2O2. Na2O2 is also a sodium peroxide, so those will be -1. And if it's bonded to fluorine, which is more electronegative than oxygen, you can expect the oxidation number to be slightly different. For the case of hydrogen compounds, we would usually be accounting for it as a +1, but exceptions are like metal hydrides, such as sodium hydrides, lithium hydrides, as well as what you have learned in organic chemistry, such as in the case of lithium aluminium hydride, sodium borohydride, the H is also at -1. The last case that we have that's easy to classify would be the group 17 elements of chlorine, bromine, and iodine. So these are usually at -1, except when they are bonded to more electronegative atoms such as nitrogen, oxygen, or fluorine, as well as it could be by themselves. For example, if there is a Bri, right, you attribute the iodine to be at +1, bromine at -1, because of the difference in electronegativity. Bromine is more electronegative in that sense. The fourth rule is on compounds or molecules, right? They are neutral. So we can actually account for the sum of all atoms to be 0, sum of the oxidation number of all atoms. So with that, we can take an example of uranium in this case. For potassium, we can account it as +1, X for uranium, and -1 for the fluorine. So this compound here, overall, or rather the sum of all the oxidation number will be 0. We can have a simple algebra algebraic equation like this to solve for x as the unknown, and that will give us an x as +3. That will be the oxidation number of uranium. For polyatomic ions, the sum of oxidation number of all atoms are equal to the charge on the ion. So we take an example of this chromate ion. Let the oxidation number of chromium here be x, oxygen will be -2. So again, we form a simple algebraic equation here. We can solve for x as the unknown as +6. So in this case, the oxidation number would be of chromium will be +6, and this is actually, you would account for it as a chromate 6 with a Roman numeral, okay, ion. Okay, now that you have done all this, you could try self-practice 1 before we carry on.
We are now exploring the rules regarding oxidation number involving covalent molecules. So we will start off with carbon dioxide, keeping in mind the three most electronegative elements are fluorine, oxygen, and nitrogen. So if you take a look at carbon dioxide, you see that each carbon and oxygen shares a total of 4 electrons per bond. So you might want to draw the 4 electrons on carbon and oxygen, between carbon and oxygen. So you realize that because oxygen is more electronegative, the 4 electrons, 2 being contributed by carbon, the other 2 being contributed by oxygen, spends a greater deal of time with the oxygen atom, owing to the fact that he's more electronegative. And because of this reason, it can be seen that oxygen made a net gain of the 2 electrons of carbon. And because electrons are negative, therefore the net gain of 2 electrons gives oxygen an oxidation state of -2. Carbon has made a net loss of 2 electrons from the relationship with this oxygen atom on the right. He does the same thing again for the oxygen atom on the left. He loses another 2 electrons to the oxygen on the left. So a grand total of 4 electrons were lost in this particular example. Because he lost 4 electrons and electrons are negatively charged, he is assigned an oxidation number of +4. Oxygen contributed only 2 in this relationship. However, 4 electrons spends a greater deal of time with him, owing to a greater electronegativity. And because of that, because he has a net gain of 2 electrons, therefore his oxidation state is -2. Now we move on to the next example. In the next example, carbon and carbon has equal electronegativity. And because he has equal electronegativity, therefore there is no difference in terms of electron movement. The electrons are shared equally between both carbon atoms. So starting with the carbon on the extreme right, the oxidation state assigned, because he didn't make any net gain, non-net loss, his oxidation state is assigned as 0. Now, from the carbon in the star key, you would also notice that the carbon in the star key has no equal sharing of electrons with the carbon on the right. However, with the oxygen on the left, because he's less electronegative, the electron spends a greater amount of time with the oxygen on the left-hand side. And because of this reason, because oxygen has made a net gain of 2 electrons owing to his electronegativity, the 2 electrons confers an oxidation state of -2. And because carbon has made a net loss of 2 electrons, and since electrons are negatively charged, he has an oxidation state of +2. Moving on to the last example over here. So you have oxygen and oxygen, whereby the electrons are shared equally between the 2 atoms. So because of the fact that the electrons are shared equally, the oxygen on the right-hand side will have an oxidation state of 0. Now with respect to the carbon on the left, because carbon is less electronegative than oxygen, so therefore the electron spends a greater amount of time with oxygen. But you must understand that in this particular single bond, oxygen contributes one, carbon contributes the other. But the shared electron spends a greater deal of time with oxygen, so he has made a net profit of 1 electron, and therefore he has an oxidation state of -1. Carbon, if you realize, alright, because he contributed 1, but that 1 electron spends a greater amount of time with oxygen, he made a net loss of 1 electron, and therefore his oxidation state is +1. So that is how you assign oxidation states to individual elements considering their electronegativity.
There's a shortcut for determining oxidation number of carbon in large organic molecules or compounds. This is of interest to us because we do quite a bit of organic chemistry in this syllabus. So firstly, bond between a carbon and another carbon will not change the oxidation number of the carbon. It will not contribute to any change. Because these two atoms of same electronegativity, the bond will break in such a way if it's ionic, it will not change the oxidation number. Secondly, if there's a carbon and hydrogen bond, we can consider the hydrogen to be less electronegative. So in that sense, both of the electrons will be transferred to carbon when the bond breaks in an ionic manner. This gives you a reduction of the oxidation number by 1 for the carbon. Thirdly, every bond between carbon and a more electronegative element, as we have given you a whole set of examples here, right? This will increase the oxidation number of carbon by 1, because now both electrons are actually lost from the carbon in that sense, the bonded electrons. So carbon has lost an electron, it will decrease the oxidation number by 1. So with this shortcut and also the earlier a bit longer method of determining oxidation number, you could also take a look at the next page, 18-5, for a large number of examples to see whether you can fully understand this. Let us look at this work example. The hydrogen is given as +1. The oxygen is -1 because of the CO single bond. So in this case, we can consider the carbon itself first and how the covalent bond will break if it's ionic. So that's the first method. So in this sense, right, the CC single bond, you break in this manner, you go to the carbon. The hydrogen, the CH bond, carbon is considered more electronegative. It will gain both electron, okay, from the hydrogen, whereas the oxygen, the CO bond, both electron will go to the oxygen. Therefore, this is considered a zero oxidation state for this carbon. Okay, so this method is breaking the covalent bond as if it is ionic. If we do the shortcut method, the oxidation number due to the CH bond, because hydrogen here at +1, you will lose both electron, you take it as -1, right? Then the CO is only one bond, a single bond. The shortcut method will give it a +1. So in total, the oxidation number will be 0. So as I said earlier, page 18-5 has many such examples using these two methods. You could consider them to see if you fully understand. So work example part B, right? The carbon, okay, the answer we have will be at +2. It's because of the Br bond, they are -1. So if you take the method of breaking the bond as if they are ionic, consider the electronegativity, this will be the both electrons gained from the CC double bond. So out of these 2 electrons, it's supposed to have 4 valence electron, right? But there's only 2 electrons remaining, you give it a +2 charge. So this is what it means here, there's 4 valence electron. If you see the example in page 18-5, they all start with 4 minus something, right? So how much electron is currently present now? Is it 4 or is it more than 4 in that sense? Or less than 4? If I do the shortcut, it'll be a little bit easier. It's +1 each, right? So it's actually +2 for the oxidation state because each bromine contribute to +1 for the carbon. So example 3 here, even more straightforward because the C triple bond N here, the CC bond, if I take the shortcut, it does not contribute to any electron or rather change in oxidation number in that sense. So using the shortcut will be quite easy here, and it will be a +2. Okay, let's carry on to the lecture practice, okay, to see if we can fully understand. Maybe you take a pause here and give it a try. If you have tried the lecture practice, okay, part A and B are given here as an example. If you have done the shortcut method, you attribute +2 and +1 each, right? Because of the oxidation number that you do to oxygen. There's two CO bond in that sense. Okay, if you have taken the method of shortcut method, there will be +2 due to this oxygen CO bond, two double bond CO here in that sense. Whereas for chlorine, right, you account for it as +1. Whereas the other case, for part B, okay, because there's only one CH bond here, if you take the shortcut method, it will be -1. So indeed, the shortcut method is a little bit easier to get us to the oxidation number. Okay, let's consider part C and part D. If you have taken the shortcut method, right, it will be just +2, +2, because each of this, the CN double bond in that case, right, and the CO double bond. Okay, if you have taken the longer method, it's still the same outcome because all the bonded electron now goes to the more electronegative N and O respectively. The last one is an A-level example. So the exact A-level question is just to state or suggest the oxidation number of bromine. What it requires you to recall and understand is that the electronegativity difference here. So simply both electrons would move towards your nitrogen, right? So in that context, you expect your bromine to be at a +1 oxidation number. And if I take the longer method, it will be 7 minus 6, which is equals to +1. So if you're not dealing with carbon, knowing the exact method of breaking the covalent bonds as if they're ionic will be helpful, provided you are very clear of the difference in electronegativity. Okay, now that we have done the oxidation number recap, we also want to recap what is a redox reaction, which involves transfer of electrons, right? We may define this in terms of that, and that's important for us as we are looking at loss of electrons as oxidation, while gain of electrons as reduction. So you see half equations like that quite a bit in this topic. Okay, of course, you would have remembered this from O-level as well. The idea of oil rig, where oxidation is loss and reduction is gain. As far as possible, we want to define redox based on this concept of electrons transfer. Okay, it can also be defined in terms of oxidation number change, and that's why the recap earlier. And this is quite important as well. Often at A level, you're asked to maybe state the oxidation number and hence determine what reaction it goes through. Okay, we'll look at that at work examples and lecture practice at the next page. So if we take this example here, as in your notes as well, this is a reduction reaction that's happening where lead, right, is reduced, okay, where there's a decrease in oxidation number from +4 to +2, and the iodide, okay, is oxidized to iodine because the oxidation number has increased from -1 to 0. Next, we are looking at disproportionation. If some of you don't quite remember, this is a simultaneous oxidation and reduction of the same substance that occurs. Okay, so in this case, let's look at nitrogen in this sense, or the nitrous acid in this case, okay, or you can term it as the +3. You can see that when it gets to a nitric acid, it's at +5, and NO is at actually a +2 oxidation number. So in that case, when this occurs, it's a disproportionation that gives you the nitric acid as well as the NO, an oxidation and a reduction that's occurring at the same time. Alright, now let's look at the work example to have a clear-cut understanding that's involved. Okay, the first up would be silver metal and chlorine. As stated already in your notes, this is the change in the oxidation number that's involved. So clearly what is being oxidized here is silver, because there's an increase from 0 to +1. Whereas for chlorine, there's a reduction of 0 to -1. The next example that we have is the case of your sulfur dioxide and chlorine gas. So that change is from +1, right, all the way to, from +4 to +6, and the chlorine is from 0 to -1, so that's the reduction that occurs. Alright, next we are going to look at the lecture practice 2. So give yourself some time to do it, and we'll look at it in the next video. Okay, for this lecture practice, of course, you must be very clear of the oxidation number first, then we can carry on. Okay, so I hope you have achieved the oxidation number here. Right, oxygen is at -2, so this will give you this iodine in this ion as +5, as overall is -1, whereas the elemental iodine is 0, so from -1 to 0 in that sense. And chlorine is at 0 to -1 and +5 in this case. So this is option B here, right, or rather part B. It is a redox reaction that's of the same substance, Cl2, so this is actually a disproportionation that's occurring. Okay. Now, part C, in this case, there's actually no change in oxidation number. They are in your usual oxidation number that's involved. There's no special case of hydrogen becoming hydrogen gas or hydrides, oxygens becoming peroxides or oxygen gas. The metal also remains as itself, sulfate remains as 2-. So this is actually a neutralization and there's no oxidation involved. Okay. Okay, we're going to explore here what's an electrode potential and how does it come about. Alright. So firstly, if we place a strip of metal in a solution of its ion, okay, you expect two reactions that could be happening, or they do take place, they're opposing reaction. One is a reduction, the other is an oxidation. So reduction of the metal ions could take place by gaining electrons from the metal strip and becoming the metal atom itself, or it could be an oxidation that's occurring whereby the metal atoms loses an electron behind and comes out to the solution as metal ions. So these two reactions are occurring at the same time if we place a strip of metal in a solution of its ions. While having said that, we can represent this as an reversible reaction. So there we go, we have an redox equilibrium established between two redox species that are related to each other. In our example here, is the metal and its ions. Okay, this was the first example that were given historically. At the same time, this let us understand what we're going to explore on electrode potential. So there is a potential difference that's between the metal and its ions, and we know this as the electrode potential. The units given are in volts in your data booklet and commonly used as convention. It's written as the species to be reduced and the reduced species. So in this case, the ion is to be reduced and is reduced to the metal atom itself or the metal solid itself, right? So this gives us an idea of potential or a measurement of how likely this reaction is going to occur. Okay, so with that, at the same time, we can consider this setup that was mentioned earlier, right? A metal strip into its ion solution as a half cell, and there are many kinds of half cells that we'll look at later on in 3.3 that can be between any two species that are related by redox half equation. Okay. Now, by convention and in data booklet table 4a and 4b, the half equations to represent the electrode potential values are written as reduction as the forward reaction. So reduction is the forward reaction. The main thing to understand, remember here is this is the way to write it. You should always write it like that. The value that's given, this electrode potential value that's given, will represent forward as reduction. The more positive, the more likely the reduction would occur. Okay, this is important by convention and not to reverse this anyhow. Okay, and the value may be positive or negative depending on the position of equilibrium. So the more positive the value means the forward reaction is more likely to occur. The position of equilibrium lies actually more to the right. That means the reduction process is more favored. Whereas the negative value, on the contrary, would be the position of equilibrium lies more to the left. So the reverse reaction is more favored. That's the oxidation process. So do keep this in mind as we move on to understand the factors affecting the electrode potential. Okay, because electrode potential values represents equilibriums, redox equilibriums in that sense, the position of equilibrium can be affected by many factors that you're already familiar with. So specifically, we start off with the nature of the metal. Okay, because in this case, it's like different reactions would have different equilibrium constants. In this case, for different metal, if the reactivity is different, it will also have a different electrode potential value. So a greater tendency to be oxidized are more reactive metal, right? That's all that metal can undergo in that sense. It wants to be oxidized. And the equilibrium position will lie more to the left, right? So very negative values here represent the equilibrium position very much to the left, as they are very reactive metal, whereas less reactive metal like copper, okay, or silver, the values will be more positive, okay, as the position of equilibrium will be more to the right. So it's in that context on the nature of metal. Now next, as specifically required in your learning outcome, so you must know this, the concentration of ions. So similar treatment to any reversible reaction, discussion about equilibrium, we look at the concentration of ions. So according to the Charteris principle, if you decrease the concentration of the ion, the equilibrium, the position of equilibrium rather, will shift to counteract that change. So now it will shift left to counteract the change on the decrease of silver plus ion concentration. You try to increase it, right? You counteract that, and then this will favor the reverse oxidation reaction. So the value now would become less positive or more negative. So do take note of this in your notes. Also note that we use the term less positive or more negative, less negative, rather than larger or smaller. Okay, this is the same concept as your delta H, delta G, because there's a positive or negative value that's involved. We want to be very, very specific about using these terms. Right, so you can see concentration decrease, it gets less and less negative. The reverse oxidation reaction is now more favored in this context. We could also consider this instead of in a metal scenario, in other kind of redox potential, okay, or electrode potential setup, half equation that's involved, and we'll learn more of this later on. But I just want to introduce here as well at the same time, if I decrease the concentration of Cl minus, the Charteris principle, the system will counteract the change to increase the concentration of Cl minus, the equilibrium position or POE now shift to the right. And to the right, it will favor the reduction reaction, right? To the right, reduction reaction going forward. Okay, so that means the electrode potential now will be more positive. So it's a very logical value. Okay, I want you to consider that. The more positive it is, the forward reaction is more likely to occur, and that's the forward reaction must be written as a reduction reaction, okay, to the right. That's similar to, or rather identical to all of the half equation written in your data booklet, table 4a and 4b. Now the last factor to consider is pressure for gaseous species. So again, same example here, and logically for gaseous species in terms of equilibrium, chemical equilibrium, you would say that if the pressure is increased, partial pressure rather of Cl2 is increased, partial pressure increased, the POE or the system will counteract the change. The POE now will shift to the right to remove some of the Cl2 gaseous particle, right? Cl2 molecules to be removed, so to decrease or counteract the change of the pressure of Cl2, so to decrease the pressure of Cl2, and that will favor the forward reduction reaction, right? Okay, so shift to the right, reduction reaction. So that will make it more positive or less negative. Okay, quite easy to remember. Shift right, reduction reaction. So the forward is always a reduction reaction. So with that, we can move on to the next concept of standard electrode potential and how we can better measure them. We have early talked about the idea of electrode potential and established it as the potential difference between two redox species in that sense, right? It can represent any half cell setup, which we'll learn a lot more later on. But we do know that there are many factors that affect electrode potential: concentration, pressure. So we want to fix those pressure and have a standard that's involved. So this standard represents the factors that we do want to fix, and the standard conditions are 298 Kelvin, 1 bar for the relevant gas that's involved, okay, partial pressure of the gas that's involved, 1 bar, as well as a concentration of ion at 1 mole per dm cube. So this is quite important to understand, right? We want to keep it as a standard condition. This is about the same as what you will be looking at delta H, delta G standard. The only difference is usually we do not include the concept of 1 mole per dm cube in those standards, okay? At the same time, because we are not possible to measure the absolute electrode potential of a metal or the ion just by itself, we can only measure it when we can complete a circuit. Basically, we earlier said that this was one half cell, right? We now have to have two half cells connected. As the half cells are connected, then we can measure the potential difference in that sense. Okay, so that's where we want to get to at the next stage. And one of it is chosen as a reference, and this reference is given as a 0 volt, which is the standard hydrogen electrode. At the same time, as mentioned in your notes, we do need a platinum electrode if the half cell system does not include a metal. But not to worry that much, we'll come to it a bit later on when we look at the different half cells. So let's define standard electrode potential. We need to be able to do that. Okay, these are the standard condition, okay, where you're looking at the potential of this electrode under standard condition relative or reference to the standard hydrogen electrode, whose electrode potential is assigned as 0. So this SHE, standard electrode potential, is assigned as 0 in terms of the value, okay? And these are the conditions that's involved. Again, 1 bar of partial pressure of the gas that's involved, okay, and 1 mole per dm cube concentration of the ions that are involved in this electrode potential or in this half cell. All right. So we also consider this as a standard reduction potential because as based on the syllabus, we do write the equation as the forward reaction as a reduction equation as mentioned earlier. So just have a quick look at the setup of a SHE. Okay, we have it in 1 mole per dm cube of H plus, standard condition. So this could be using HCl or using half a mole of H2SO4. So these are the kind of things that A-level have asked before, just to be very clear. Main thing is to get 1 mole per dm cube of H plus ion, which is the ion involved in this half equation. The H2 gas also has to be 1 bar, 298 Kelvin, stated clearly. The platinum itself is a bit special. So this is the case of, you have ions, you have gas, you still need a conducting electrode, right, for the electrons to move. So we use a platinum electrode. But in this case, we have to state very clearly, and A-level has tested that before as well. It's a platinized platinum electrode. Platinized is finely divided platinum coated onto the platinum electrode. So that allows the H2 gas to absorb to establish the equilibrium as quick as possible. Right? This is a bit about rate of reaction. It does not affect the electrode potential measurements or delta G in that manner. It doesn't, but it affects how fast you can reach that equilibrium. And that's critical in trying to do an actual experiment. Okay, so this part is pretty unique. You ought to know it quite well. And by convention, we give SHE a 0 volt scenario. Okay, I think we will take a pause here and we will come back again to look at SHE as a recap. We last left off here at the standard hydrogen electrode. What's the setup that's involved? What's the standard electrode potential in that sense as well? So this is our reference and we take it at 0 volt. Okay. Now we are going to look a little bit more into how to measure the standard electrode potential of a half cell that's of interest. Okay. So we're looking at the setup. So for this setup, the main thing that you need to have, the main three things, we start off with the SHE as explained earlier already, your 0 volt reference, right? Then we do need a high resistance voltmeter. The reason for this will be more familiar to the physics student. For us, we're not so particular about the reason for it, but we do need to label that it's high resistance voltmeter. Okay, so for chemistry here, the main thing is about the labeling that's involved. Okay, the reason is written in your notes, right? Mainly that we don't want the voltmeter to draw any current and therefore resulting in a maximum potential difference that's measured. Okay. Next, we need the salt bridge. The salt bridge of why we need salt bridge and the reason for it will be more pertinent for a chemistry student. Okay, you see over time there's a buildup of excessive charge due to either the maybe the cation produced or the cation that's lost, so therefore there's a lot of anions. It will actually result in the flow of electron to be somewhat disrupted, less and less likely for the electron to flow. Okay, so because of that buildup of charge, we end up with no flow of electrons, so the voltmeter can't measure what you need, or the electricity is not produced in that sense. At the same time, we do need to complete the circuit. Okay, so the reason number one here is to complete the circuit, yes, right? Secondly, we need to balance the charge. So this salt bridge importantly allows electrolytes, okay, ions, okay, electrolytes, ions to flow, okay, but not electron. Electron itself move through the external circuit, move from electrode to the wire to the next electrode. But ions can move between the two half cells through the salt bridge. That's also why this salt bridge is usually made up of saturated potassium nitrate solution. We choose ions that do not react or form precipitate with other ions, and we just need a strip of filter paper, or it could be a porous membrane or porous materials to set up this salt bridge so that it can prevent the ions between the two cells from mixing together, minimize it. So that's the purpose of our salt bridge, to complete the circuit, to balance the charge to maintain electrical neutrality. Okay, while doing that, you don't want the ions between the two cells to mix directly in that sense. Alright, so as earlier said, my SHE will be given as 0 volt. So with that, we can go on to consider measuring half cells. So also let's take a look at the three types of half cells that you could set up and take measurement from. So the three common type that we have is metal and its ions. So we've seen this a lot earlier also. Zinc and zinc 2+, copper and copper 2+ in that sense. Cl2 gaseous and Cl- is an example of non-metal and its ions. Alright, so usually gaseous, okay, that's the usual case. In the data booklet, we have example of your F2 gas, maybe hydrogen SHE is one of this example, non-metal and its ions. And the third examples are between two ions, so iron 2+ and iron 3+. I think there's plenty of example in the notes as well between maybe vanadium 2+ and vanadium 3+. As long as they're between ions, this is the third example we have. Okay, so the common thing among all three examples here is their standard standard electrode potential. So these are all the standard conditions as required, right? We want the 298 Kelvin, 1 bar of any gas that's involved, the partial pressure of the gas, 1 mole per dmq of the ions. One additional thing is about the platinum used as electrode for half cell that does not have a metal that's involved in the redox reaction. So basically, this example, the first one, we can use iron as electrode, not a problem. But the other two, we don't want to introduce a metal electrode that can undergo redox. So we cannot use iron in example 3, we cannot use maybe for example zinc or copper in example 2. Rather, we'll use an inert platinum electrode. So these conditions are the same as what was written earlier at page 1811. Okay, but in the meantime, also please be mindful of the platinum electrode. Do highlight it in your notes. Okay, for these two types, I will take a look at again later on. Right. So I'll take a pause here, and then we will go on to looking at the first example of metal in contact with its metal ions. Let's now look at the first type of half cell that we can set up for measurement with the standard hydrogen electrode potential, the SHE. Right. So this is a metal and it's metal ion half cell. Okay, so with that, of course, the main thing has to be there, which is including your SHE, the salt bridge. The reason for the salt bridge, it can be asked, is to complete the circuit and to maintain electrical neutrality. Next, of course, the high resistance voltmeter must be present. It might be a good idea to label your salt bridge as well. Okay, so we could label the salt bridge as potassium nitrate. Okay, and the SHE is given a standard 0 volt, and whatever reading we get at the voltmeter would correspond to the standard electrode potential of the metal and its ions, this half cell, right? Okay, so let's look at two specific examples. The first one that we can look at is zinc and zinc 2+. So not to worry about the label first, but let's follow through on how we can draw a setup like that. Firstly is to note the E value, okay, the E0 value or the standard electrode potential value. So in this case, we're expecting it to be negative 0.76 volt. This can be found in your data booklet as well, right? If it's more negative than the 0 volt, so which means that all negative value in that sense, all negative E0 value, it will mean that the reverse reaction is more likely to occur. If it's a more positive E0 value or a positive value with respect to SHE compared to SHE, okay, then the reduction, the fall reaction is likely to occur. So in this case, if it's an oxidation occurring, then the electron will be lost. Okay, not to worry about the label first. The electron will be lost. It will move through the external circuit into the other electrode, right? So we're expecting oxidation to occur. We were suggesting that because of that, the electron will be formed, okay, and it will move through the external circuit. At the same time, the physical observation you see is the zinc electrode decreasing in mass or getting thinner and thinner in that sense. While the electron move into the other electrode, the standard hydrogen electrode, right over there, the platinum electrode in that sense, you will expect the H+ ions to take in the electron and form H2 gas. So the physical observation or the observables will be bubbles of H2 gas being formed. Okay, so that's what we want to be very clear at this stage, the movement of electrons. Okay, starting from identifying what would happen at each electrode based on the electrode potential value. So we need to identify that. Then we can state clearly that, oh, this case we're looking at a oxidation over here. Then that's how the electron will move, and any physical observables that we can report as well. Written in your notes also, you have the cell diagram. Again, I'll explain in a bit how this is written or why it's written in such a manner. But at this stage, we'll just take it as a cell diagram to represent this as well. Okay. On the next slide, I'm going to try and explain to you how to remember naming of the electrodes. So as written in your notes, you see the anox and red cat. So this helps us to remember a bit easier, a little mnemonic in that sense. Anox meaning the anode, at the anode, oxidation would occur, while reduction occurs at the cathode. Okay, this is absolutely true for all types of cells, part 1 and part 2, electrochemical at part 1, electrolytic in part 2. So this is absolutely true. Alright, we don't have to know historically why it's named anode or cathode, but we must be able to remember that oxidation occurs at your anode while reduction occurs at your cathode. So the next thing that you must be able to produce and to label, okay, hence also to remember, then you can do that, is for electrochemical cells, the positive electrode is at your cathode. One way to remember that is cathode with the T, then you have the plus. So that's the plus sign. Okay. You would also, if you want to understand the rationale of it, is positive electrode because reduction is occurring. So for reduction to occur, right, you actually need the electron in that sense. So it's lacking of electrons, so there's a positive outcome. Where else negative, anode, AN, right? Anode will be the negative electrode. Again, only for electrochemical cells. Only for electrochemical cells, only for part 1. So in that sense, it's the more negative electrode. If you want a chemical reason for that, it could be because the electrons, right, are being produced at the anode. Oxidation occur, right? So electron is being produced. So as electron is produced, that gives it a more negative electrode comparatively. Okay, so do you need to explain this in depth? Not really, but do you need to remember and be able to label? The answer is yes. So you must remember this set of reduction is cathode, that's absolutely true, right? Anode, oxidation occur, that's absolutely true as well. And then be able to state positive and negative. Okay, for this electrochemical cell, this part of the topic, electrochemical cells, it will be positive is at the cathode. And hence also able to state the movement of electrons, right? Oxidation, electrons is formed, it will move to the cathode, anode to cathode, okay, in the movement of electrons. So that brings us to the other thing that is being used here that is new to you, the cell diagram or cell notation. Because back then, trying to draw a diagram and transmit a diagram is not as easy as today, where you can just take a photo, WhatsApp, right, or through email or post on the internet. It's quite difficult back then, and writing things down in a sensible way would help us to transmit this information. And what we have here is a cell diagram or cell notation. The electron flow again is from the left to right through the external circuit. So that is absolute in that sense, or that's how you would want to write it. It starts off with the left hand side, okay, as a oxidation process. So the half cell on your left is the oxidation process. Zinc is oxidized to zinc 2+. That makes sense, right? And then on the right hand side, you have the reduction process, okay, where H+ is reduced to H2 gas. So you could consider it again as a reduction process. Your right hand electrode is the positive electrode, your cathode, right? So that helps you to remember as well. The cathode, right, that's where reduction occur. That's positive, it's on the right hand side. So this whole set would help you to remember a little bit easier. Whereas the left hand side is your anode and oxidation occur. So it starts from anode and end with cathode. The electron flow, external circuit, is from left to right. Alright, so that helps us to remember this set quite well. The symbols, if it's one line, is between phase. Okay, solid and aqueous are different phase, so you have one line, and then aqueous and gas and solids are different phase. Remember to write your electrode, right? So this is one line. A double line is actually representing a salt bridge. So this is stated there as well. A comma, we'll see this in the third example cell later on. Okay, that's between of the same phase, usually in case of aqueous in that sense. And of course, there's a state symbol that's involved. So let's quickly now look at another specific example of this type of half cell, which is your copper scenario, right? Using copper and copper 2+. So I'm going to again demo starting off with how do I label all this and how do I find out. Yes, the standard condition needs to be stated very clearly, right? Your high resistance voltmeter, again your salt bridge here is good to label. So we could consider this as again a potassium nitrate salt bridge, right? And then the next step is to know that it is a positive electrode potential value. Okay, the symbol should be here. Positive standard electrode potential value for your copper 2+ to copper. Okay, so having known that already, I will decide that it has to be the case of a reduction occurring at that half cell, right? Because the positive value, the forward reaction is more likely to occur. So that's a reduction happening. Once I know it's a reduction, I would decide that I require electron for that reduction to occur. So if I require electron, it has to flow in, right? So now the electron will flow out of the SHE into the half cell, the cathode, copper cathode in that sense. Okay, having said that, I'll also know that oxidation will occur on the other electrode. So that's where I know the oxidation occur. I can label it as anode, and it's a negative electrode. That's where electron flows out. So I start off with knowing that this is the reduction. Copper side is the reduction. Being the reduction, that will be where your cathode will be named. That's where your electron will flow in, because you need electron for the reaction, and it will be the positive electrode, right? With the naming of cathode, or you could consider electron is to flow in, is lacking electrons, etc. Okay, so that's how we can label and draw a diagram successfully, and the physical description follows through as well. Now in this case, your copper electrode will increase in size or mass, and the blue solution of your copper sulfate will fade as the reaction proceeds. And on the other side, there's no hydrogen gas involved. Okay, hydrogen gas is being used in that sense, so you will not see any effervescence or bubble that is occurring as hydrogen gas is being pumped in, is being used. But of course, the pH actually would decrease as more and more H+ is being produced. With that and this 2 half cell, we can consider a bit of the thinking time that's involved. Let's take a look at this, right? Which one is more easily reduced then between these 2 half cell? Okay, this is under your thinking time 1, under the same page. So if you consider the values, I hope you got it right. The more positive one will be reduced. So in that sense, okay, and what will happen when these two linked up? Well, since copper 2 plus is more easily reduced, it will be reduced, and the zinc metal will be oxidized. And this is something that we'll talk about later, called a Denel cell, in the later part about a galvanic cell application. Okay, so keep that in mind first for now. Okay, so I hope from the earlier video you understand very well now how we can determine what's anode and cathode, and how this can occur between 2 half cells in that sense. So we can look at the next type of half cell that we are looking at, which is between a non-metal and its ion. So the example we have here is chlorine, okay, gas, and Cl minus. This is the setup that we want. The first thing that you notice is difference is that we will need a platinum electrode here, right? Because we don't want any of the metal, reactive metal involved in this half cell. And again, similarly, we would first trying to understand what is the standard electrode potential value for this half cell, okay, which is a positive value once again. Then we can decide that, oh, that's the case, the electron must flow in. Okay, again, I would encourage you to label your salt bridge with it as KNO3. Okay, so we can decide that, so back to this, we can decide that electron flows in, right, in this manner, into this electrode. So if electron flows in, I can call it a cathode, right? Reduction occurs right at the cathode, and I can label it as a positive electrode. All right. Some of the physics students might remember easily that electron flows out of a negative terminal to a positive terminal. That is fine as well. Okay, no problem in this case for you to label it accordingly. In the other side, at anode, the oxidation occurs. So electron is produced, right? It moves out. So that's where it will consider the movement of electron as well. And oxidation, I'll name it as anode, and it's a negative electrode for electrochemical cells. So with that, the observables that you want to be able to see is actually no bubbles that's being formed at both electrodes, because both sides the gas is actually being used up to give you the ions. So if anything, you would expect the H plus concentration to increase in the SHE. Perhaps if you have a pH meter, you show that pH decreases. The cell notation, as explained earlier, will be written in a manner like this, right? Where you go from left to right, anode first, negative, showing the the oxidation process, anode, oxidation process. Then the cathode, where is the reduction process. So A to C, anode to cathode, that's the electron flow as well. So that helps us to remember that. Okay, the negative electrode is the one where electrons come out, right? Negative electrode is at anode, and positive electrode is at cathode. Again, if you are a physics student, you might, or if you remember back when you learn physics, battery, the negative terminal is where electron flows out. That might help you as well. Okay, we'll also now take a look at the last type of half cells that we have. Okay, if it's the same element, okay, but they are ions. The main thing is we are only looking at ions, right, and different oxidation state. So the example here that we have is iron 3 plus and iron 2 plus. So the difference now is you don't see, as compared earlier we have to bubble in gas, right? So now you don't need the gas, okay, unlike the SHG one where you still need the H2 gas to go in at 1 bar, etc. But you do need an inert electrode. Okay, please be mindful here, as the common mistake is to use an iron electrode, which should not be the case, as your iron is not the half cell that you're trying to measure, or the half equation that you're trying to understand to find what's the standard electrode potential. What you're trying to set up here is actually between the iron 2 plus, these two ions, okay, and iron 3 plus. Alright. So with that, same thing, we first decide what is the standard electrode potential, or if you are given a hint, or we can find the value, which states here positive 0.77 volt. So that's your voltmeter reading that you expect. And with this, we'll know for sure that a reduction is going to occur over at this electrode. Since it's a reduction, electron must flow from the other electrode, the SHE, into this platinum electrode in your iron 3 plus, iron 2 plus half cell, right? So again, if you're a physics student, or if you remember, you say negative, that's where electron flows out. Positive is where electron goes in. If not to worry, we are quite clear. Oxidation occur, you must call it an anode. Because an anode is where oxidation occur, we also remember that it's negative for the case of the electrochemical cells. Okay, electrochemical cell in this case. And then the other side would be where the cathode goes in. I think we have missed the label of the salt bridge here, so do label it as the salt bridge. Again, potassium nitrate is the best option, okay, to label this as salt bridge, and the cell diagram will be written as such. Okay, and also not to forget here the observation, after some time the yellow solution would fade. Again, no bubbles on the hydrogen side because the H plus is produced. Okay, so maybe pH will decrease at the SHE if you use a pH meter. And on this side, the iron 2 plus, iron 3 plus scenario is that the iron 3 plus will react away, so the yellow color of the iron 3 plus will fade with time, maybe to the extent where you see more of the green color of the iron 2 plus as well. Alright, and the cell diagram is written as such, again left to right, clearly in this manner. Okay, that's where the electron flows occur. Okay, so that sums up our part here on measuring standard electrode potential, the setup, as well as labeling of anode, cathode, positive or negative, flow of electrons, and importantly in this all this label, okay, at the same time to decide whether, starting off with whether is it a reduction or oxidation occurring. So now you have the skill set to label two half cells, to decide electron flow, to decide cathode, anode, positive or negative, right? And then to write even the cell diagram in that sense.
You probably know the feeling. Your phone utters its final plaintive bleep and cuts out in the middle of your call. In that moment, you may feel more like throwing your battery across the room than singing its praises. But batteries are a triumph of science. They allow smartphones and other technologies to exist without anchoring us to an infernal tangle of power cables. Yet even the best batteries will diminish daily, slowly losing capacity until they finally die. So why does this happen? And how do our batteries even store so much charge in the first place? It all started in the 1780s with two Italian scientists, Luigi Galvani and Alessandro Volta, and a frog. Legend has it that as Galvani was studying a frog's leg, he brushed a metal instrument up against one of its nerves, making the leg muscles jerk. Galvani called this animal electricity, believing that a type of electricity was stored in the very stuff of life. But Volta disagreed, arguing that it was the metal itself that made the leg twitch. The debate was eventually settled with Volta's groundbreaking experiment. He tested his idea with a stack of alternating layers of zinc and copper separated by paper or cloth soaked in a saltwater solution. What happened in Volta's cell is something chemists now call oxidation and reduction. The zinc oxidizes, which means it loses electrons, which are in turn gained by the ions in the water in a process called reduction, producing hydrogen gas. Volta would have been shocked to learn that last bit. He thought the reaction was happening in the copper, rather than the solution. Nonetheless, we honor Volta's discovery today by naming our standard unit of electric potential the volt. This oxidation-reduction cycle creates a flow of electrons between two substances, and if you hook a light bulb or vacuum cleaner up between the two, you'll give it power. Since the 1700s, scientists have improved on Volta's design. They've replaced the chemical solution with dry cells filled with chemical paste. But the principle is the same. A metal oxidizes, sending electrons to do some work before they are regained by a substance being reduced.
Okay, hope that you have seen the TED video that we posted up earlier, about 2 to 3 minutes, where the first 2 to 3 minutes it talked about the origin or the discovery of battery in that sense. So I will not belay the point and go through the entire history review. But for this part, we do want to consider a setup of a galvanic cell as an example of an electrochemical cell, right? So this is a very practical application rather than just looking at electrode potential and what's the purpose of it, how to measure it. We now have that ability or that chance to have a very practical application of it. So I'll go through much of this in a very quick manner, as we have done the main bulk of how to name anode, cathode earlier and the purpose of all this different setup. Okay. Firstly, there will be an observation where the light bulb glows. The light bulb glows, showing that there's a movement of electron through the external circuit. We label the zinc electrode as an oxidation. We'll come to it later, why is there oxidation occurring here. But once we know oxidation, we can say it's an anode, it's a negative electrode. Electron will be produced, so it will flow out of the circuit towards the other electrode, where we can label it as the cathode, where reduction occurs, right? Your red cat. And then that's also where the positive electrode is. You could also consider that electron flows out of the negative into the positive terminal. Okay, if you are remembering from a physics point of view in that sense. Okay, and in this case, electron flows in for the reduction to occur. Some more physical observation: the blue color of copper sulfate would fade over time. The copper electrode would get thicker or increase in size, while the zinc electrode would decrease in size. This is the overall equation. You see this on the next page. You don't have to copy it down. Okay, so this is looking at the application. Of course, there's a salt bridge involved, so that's quite standard. So instead of a voltmeter, now you have a bulb to show that the electricity do flow. One other kind of setup that you might have to chance upon is actually using a porous disc or a porous membrane, okay, rather than the filter, paper, salt bridge kind of scenario. So similarly, what we're trying to explain here is also written on the next page of your notes, 1819. Okay, it's trying to be more specific in this example. How come we need that salt bridge? You see, when zinc 2+ build up at one side, there's a surplus of it. This half cell is getting increasingly positive. The electron will slowly not want to move away. While the other side, the removal of Cu2+ result in a surplus of sulfate 2-. So this side is getting increasingly negative. So the electrons may not want to move in as well. So voltage, or rather the current flow, may come to a halt, right? So we want to ensure electrical neutrality on both sides. We might allow the anion, the sulfate anion, to flow to one side, and the cation, the zinc cation, to flow towards the other side. That's one possibility. Another possibility is to set up using an electrolyte, right? Potassium nitrate, salt bridge, filter paper kind of setup per se. Okay, and then that allows the nitrate, the NO3- to flow into one side, okay, to maintain electrical neutrality, while the potassium plus, okay, potassium cation will flow to the other side to maintain electrical neutrality. Okay, so this is just a very specific example to go in a little bit more depth in case you do need to explain the salt bridge to some depth in that sense. Okay, so do understand this. Okay, so the two main functions remain the same to complete the circuit while preventing any direct mixture of the two solutions in the two half cell. So whether you use a filter paper or the porous membrane, there's the same purpose, and to maintain electrical neutrality. Where else the overall reactions as such, the oxidation reduction occurs. And with that, we can move on to why can't the reaction be reversed? Why not, zinc here? Can't zinc 2 plus be the one being reduced? So that's where we can go to the next segment to decide what's the basis of the electrochemical reactions that's occurring. So in that basis, we need to look at, so this is your next page, 1820, the standard electrode potential, right? We need to know this very well, or we can find this in the data booklet. So with this, clearly the more positive one, okay, so now it's not just comparing to 0, it must be the one that's more positive, would be the one that reduction is occurring. 4 reactions occurring, more positive, right? So if reduction is occurring in one of the half cell, the other one, the more negative one, would have oxidation occurring. So that gives us the overall equation as such. Okay, so that's the basis of predicting this. Okay. We have done quite a bit earlier on to understand electrode potential, considering what is the standard electrode potential, what are the standard conditions, how to use a SHE as a reference to measure against it, how to set up different kind of half cell. There's 3 different types. Then just earlier a bit, we considered combining 2 half cells to generate some electricity, right, which is our electrochemical cell. Now at this stage, we want to understand standard cell potential. Okay. Firstly, there's a potential difference driving the electron, like in this example, from the zinc rod externally to the copper rod. So that's where electricity occurs in that sense, electron movement. And this potential difference is known as the electromotive force. So EMF is a term that is more of a physics term, but we do need this for our definition in a little bit. At the same time, there's this equation that we must remember and must be able to use. Okay, so I'll come to the use in a while, but as in this example, you could decide that the electrode potential of the reduction half cell, positive 0.34, and the oxidation half cell, negative 0.76, can be applied and used. But again, do not flip the sign. This is something that I will stress again more later on. So the definition of the cell potential is as such, is the EMF of a galvanic cell which consists of 2 half cells. So this idea of galvanic cells could be voltaic cells, could be electrochemical cell, they all mean the same thing, under standard conditions, which we have done earlier, and the difference between the 2 standard electrode potential, that is the potential difference, right? This will give us our standard cell potential, the standard cell potential. Okay, so you do need to know this definition as required by the syllabus. Define this term. This equation is of importance to us and very commonly used, so we want to get this in place. Firstly, it's independent of the number of electron transferred. So similar to your scenario where you're looking at multiple electrons, like this case you want to multiply by 3 times, the E0 value will still be the same as 0.34 volts. Okay, so do not go and increase this by multiplying by 3, we'll still use the value as it is. So regardless of your balance equation, how many more electron transfer, how many moles, we will still sub the same value. So we take a look at this example with the case of copper and aluminium in a while. Before I moved on, a positive cell potential overall is spontaneous. This is what you expect for electrochemical cells for this part. Okay. However, we do some calculation as well to show that it's negative, and those kind of case is a redox reaction that's non-spontaneous. Okay. For electrochemical cell, the redox reaction is definitely spontaneous, so the cell will work. But there are reactions that we will calculate later on to show that perhaps this redox reaction will not occur. It's non-spontaneous. And finally, if E0 cell is shown to be 0, it means that the equilibrium is established. So it's at equilibrium now. Okay, So as in this two example, you realize that to write a balanced equation, I got to multiply the first half equation by 3, the second half equation by 2, right? But in terms of the calculation, it's independent. Okay, so the values that we have, we can take it from the data booklet table. Okay, but we know that this case is a reduction, while the other case is an oxidation. So we again explained earlier in just about at 4.2, right, about the basis of predicting electrochemical reactions. So in this case, we are using this as an example of two half cells, and we can put it in and calculate accordingly. Again, there's no multiplication or no multiply this by any value. Negative 1.66 as well, you do not multiply by any value, you just use it as it is, regardless of the balance equation. Okay, so it's independent of the number of electron transfer. We sub the value as it is. And secondly, do not flip the negative sign. Alright, some textbook may tell you to do so, but not for our case. We'll leave it as it is. So use as it is, do not change the sign. This is an important note that we have put down multiple times because this is a common mistake by students as well. Okay, so we're going to go on and look at some work example next. So in this work example, we're going to do 4 parts to it, right? Trying to find the cell reaction, the cell EMF, the direction of electron flow, and also the cell diagram notation. So the cell diagram notation or cell diagram in short, right? This is something that we have done earlier, but also stated just on this page as well. So as a quick recap, and you can use it easily. Okay, so with that, firstly we decide, right? The more positive value, in this case, both are negative, yes, but the more positive one is where reduction occurs, right? We have done that very early on when we try to measure the standard electrode potential of zinc and zinc 2+. We explained that. So with that, since it's more positive or less negative, reduction occur at the nickel 2+ and nickel, whilst oxidation occur at iron 2+ and iron half cell. So you realize that this is a skill set that you need to quickly identify. If you have 2 half cell, what would happen at each of the half cell? And we can use the equation now to put the formula inside. We can also decide that the reaction, right, the overall reaction that's happening is nickel 2+ reduced, iron metal will be oxidized. Okay, the reverse of this will happen for the iron half cell. Okay, so with that, again 2 electrons, so you don't have to do any stoichiometry multiplication. They'll cancel each other out. You can just sub in to get the cell reaction. And we'll sub the value in. Do not swap the value. Do not, just keep it as it is as you have found from the data booklet. Okay, A-level does the same as well, so we are very confident about that part. Do not swap it. And electron flow is indeed from anode to cathode, so A to C, or you could remember anode, that's where oxidation occur, right? So oxidation occur, it means that you would produce electron. Producing the electron, it would flow into the nickel cathode for electron to be used for reduction. Okay, and the cell diagram in this case, again, because of the electron flow direction, we are able to quickly write down, right? That's the case from your iron to nickel. So your oxidation occurs first, the single slash for the phase difference, the double slash for short bridged, and then you go on to the case of your nickel at the other side. Okay, so now let's look at lecture practice. Let us look at the lecture practice. I'm going to pause a little bit here. You could pause and I'll carry on in the next 5 seconds. Hopefully you have attempted lecture practice. Okay, so first decide that it is being reduced. Which is the one that's being reduced or oxidized? The one that's more positive, right? Or less negative? That's the one being reduced. So we have decided on that. The reduction occurs with your vanadium 3+ and 2+. These are the ions. These two are ions, right? Half cell, oxidation occur at the other half cell. So that's where oxidation occur. Then we can write the overall equation. This case, do take note, 2 electron, 1 electron. You need to do a bit of multiplication to ensure that the number of electrons do cancel out at both sides. Alright, next will be deciding the value that's involved to sub in. So reduction, negative 0.26, whereas oxidation, negative 0.76. Sub the value as it is, you get a positive 0.50 volt. Again, reminder, you must put the positive sign, same as delta H, delta G, delta S. The signs are important, so we'll use more positive, more negative, and also remember to put the sign. So clearly, the electron flow will be from zinc to the platinum cathode. So this part is what you might not be very clear, okay, and you will say that maybe from one half cell to the other, that's perfectly fine in that sense. But if it's looking at the electrode, it's a platinum electrode. Okay, that makes a difference because we're going to write the cell diagram next, right? You must understand that this example of two ions in the redox half equation, these two ions will require you to have an inner electrode. Same as the case of a gas and an ion, you also need to have a platinum electrode. So with that, also the comma sign comes in for cell diagram, similar to earlier with the case of two ions in iron 3 plus and iron 2 plus for measuring standard electrode potential. So the comma comes in because they are in the same phase, but they are just separated as two different species. Whilst this different phase will have a single slant arrow or straight arrow, single slant line or single line. The double line would indicate swap bridge. Similarly, anode to cathode, A to C, or that's how the electron flows. We're now looking at the uses of your standard electrode potentials. Firstly, of course, it can be used to determine the standard cell potential or EMF, which was done earlier and we'll do more at a later lecture practice. Next, we look at displacement reactions and specifically whether a more reactive metal can be spotted easily. So this more reactive metal can displace cations, right, of other metals. And how do we do that with the electrode potential values? So a more negative electrode potential value means the reverse reaction is more likely to occur. The reverse reaction is of course the oxidation reaction. So in that sense, a more negative value will be able to oxidize itself, be oxidized, while reducing the cations of other metal that have a more positive electrode potential value. So these are the two examples that we think will happen, and we're now going to look at them specifically. But I'll give yourself some time to fill in the electrode potential value. It's left blank there. You could use the data booklet or you could use the table in the same page. So this table on the same page is actually some selected value from table 4b. So there's two tables in the data booklet. 4a contain much more electrode potentials arranged alphabetically. 4b is a slightly smaller selected values and is arranged in terms of a decreasing electrode potential values, decreasing. Okay, and that's the opposite of an electrochemical series at O level. Because at O level, you would say you would start putting the more reactive metal on top and then go all the way to hydrogen, then you go to copper, right? So this is an opposite direction in that sense. I have selected some values from 4b, not all the values, as there's limited space. So I hope you have picked out the the electrode potential values as required for the discussion. So firstly, we would have to look at copper and zinc here. And indeed, zinc is more negative, the value more negative, so it will be able to be oxidized while at the same time reducing copper 2 plus. So therefore, this displacement reaction can occur. So without going to the depth of the calculation, what we are saying here is that just by observing a more negative value on species on the right hand side, it would be easily able to react with the species on the left hand side or displace them in that sense, right? So for example, if you consider group 17, fluorine would displace Cl minus and chlorine would displace Br minus, so and so forth as well. So let's look at the second example, another metal, but this time we're looking at zinc oxide. Okay, zinc oxide is represented by zinc 2 plus, whereas magnesium metal, whether magnesium metal can react with zinc oxide in this manner, displace it, and produce a new zinc metal. Yes, indeed, more negative value, so it will displace it. Okay, there's one more good use of this is to consider it in terms of the acid reaction, H plus ions, right? So unlike the electrochemical series we're looking at above the hydrogen in the table, in this table 4b, we're looking at below the hydrogen in table 4b. Actually, this metal will reduce H plus to form hydrogen gas. Okay, there's a video to take a look at it in a bit. Okay, at the same time, let's look at the value in that sense. So we took two examples here. So they're both below hydrogen, right? So that means that negative, anything that's negative in terms of electrode potential value will definitely react with acid, H plus. That makes sense, right? At the same time, it also gives us a sense of this reaction with acid and which one is more vigorous. So later, if you look at the video that we have, it's comparing magnesium, zinc, iron, as well as copper, which seemingly no reaction is occurring. So do take a look at the video. Before we go there, let's look at the work example, right? Before the work example, let's look at one more concept. The strength of oxidizing and reducing agent using the same table. So the oxidizing agent itself would be reduced. So they are all found on the left-hand side of the table. Okay, so that's something that I think we all want to take note of. It's found on the left-hand side. While the reducing agent, again, reducing very nicely on the right-hand side. Reducing agent itself is oxidized, is found on the right-hand side. The more positive, the more likely the fall reaction will occur. Therefore, it's a stronger oxidizing agent. The more negative, the more likely the reverse reaction will occur. Greater tendency for it to be oxidized. So it's a stronger reducing agent. So based on this table and as illustrated for you already, it looks like this. And I use the word stronger, but here I think you're safe to put it into strongest as F2 or fluorine gas is the strongest indeed in the entire data booklet. But at table 4a, there is a species that is in fact the strongest reducing agent. That means having a more negative electrode potential than potassium here. So go look for it, see if you can find it at table 4a in your data booklet. Okay, if you do find it, you realize that it is the lithium metal in that sense. Hence also our lithium ion battery that we're using on day-to-day basis give us a rather high potential difference. Okay, so go to take a look at that in the table. Let us move on to a work example. So this is on your next page. The work example, arranging in terms of oxidizing power, so itself is reduced. So based on this table, right, you will have to pick out the value. So you could go through the data booklet to find it, or we have already written down for you. These are the value involved. So there's no doubt these are on the left-hand side. Okay, and then you have to pick out the value accordingly. Therefore, you could substitute in and have the discussion of more positive value that will result in a stronger oxidizing agent. So it should be arranged in this order, right, in terms of increasing order. Whereas the reducing power is under the standard condition, right, and more negative, stronger reducing, and you can put them in this order. Just to be very mindful of where do you find this species, these are on the right hand side. Because for some cases, example like iron 2 plus, you can find it on both left and right, so you must pick that on the right hand side. Okay, I'll show it to you on the table that we were using in just a bit, right? This table, you can see iron 2 plus here, iron 2 plus here, as well as iron 2 plus here. So if you want it as a reducing agent, you need to find it on the right hand side, while this case, you'll be having a discussion of iron 2 plus as an oxidizing agent. Okay, just to be mindful of that, where you pick them out. Okay, with that, do give it a try for your lecture practice. I'll pause for about 5 seconds for you to give it a try. Do pause the video as you attempt the lecture practice. So for the lecture practice, I hope you are able to pick out the value from your data booklet. Table 4a. Alright. Again, these have no doubts. These are the values that you can find easily, as they are all found on the left hand side in that sense. Okay, so they are looking at oxidizing power, so itself is reduced. So you want to find all these species on the left hand side, and you'll be able to order them in this order. Okay. And again, there's a little bit of difficulty in 4b. If you don't find the correct value for the case of your chromium 2+, you want this on the right hand side. Okay, so especially your chromium 2+, I'll not over explain this. I think you'll find it in your data booklet that you can find chromium 2+ on the right and also on the left. Okay, so you do have to pick out the correct value and to make use of it. Alright, the metal you have no doubts, definitely they are on the right hand side. In this case, the more negative is stronger reducing agent, so it should be in this order. Okay, next we are going to be looking at how to predict spontaneity of a redox reaction. So that involves whether is it spontaneous or not. So we're going to do a prediction here. I think we have earlier touched on these three concepts, right? Where if it's more than 0, it will be a spontaneous reaction, less than 0 will be non-spontaneous, and if it's at 0, you consider it as at equilibrium, right? This was done earlier at page 1821, and exactly do note that this is a learning outcome that's required using these standard cell potentials to predict spontaneity of a reaction. So let's look at the work example to do this. Right, we need relevant data in data booklet to decide. This is different from looking at half cells. Okay, this is not about two half cells connecting together, so you do need to focus. It's a bit different from what we have discussed earlier. Here you already decide what will happen. So the I2 will undergo reduction as shown in the equation, and the Fe2+ will undergo oxidation as shown in the equation. So while you can pick out these two half equations and its relevant electrode potential value, you cannot decide how to substitute them in as if they are half cells, right? You can't do it the same way as we have done in section 5 earlier. They are not half cells. Basically, you have already decided which one is undergoing reduction, which reaction or which half equation is undergoing oxidation. So with that, the reduction one is positive 0.54. You need to sub that in. Oxidation is positive 0.77. Again, do not flip the sign. Do not swap the value or the sign in that sense. And then what you get now is negative 0.23 volt. And that is less than 0. Hence, it is not thermodynamically feasible and not spontaneous at all. Alright, so this is not spontaneous. That's the key thing that you need to answer in the upcoming lecture practice. So we'll give you a bit of time. Again, do pause the video and try and complete lecture practice 5. Okay, let me move on to show you lecture practice 5. So lecture practice 5 in part A is a similar context here. We do have the equation already written out. You can see that the H plus here is not undergoing any redox, right? H plus to H2O, there's no hydrogen gas produced per se. And what we are considering is the dichromate and the I minus. So you have to pick out the relevant half equation as required first. So these are the relevant half equation that you will be able to find in the data booklet. Alright, and having said that, again, despite that it is multiplied by 6 here, you do not do anything to the electrode potential value. Don't go and multiply by anything. But the skill set here is to decide and substitute the reduction that you hope to happen is the 1.33. Oxidation is 0.54. So you should get a positive value here of 0.79. Alright, so next we'll look at part B. First we have to state that this is greater than 0 volt. Okay, you do have to fill in that and to state that it is spontaneous. Okay, for part B, the question is a little bit different here. It stated is the KMnO4 reacting with the H2O2. So we have already given you the MnO4 minus reduction equation, so quite clear. Now the difficulty is there are many H2O2 equations to pick. Which one to do so? Okay, clearly if this is the one undergoing reduction, your H2O2 must be undergoing oxidation, right? So in your data booklet at page 47, you will see these two values to consider: H2O2, right, acidic scenario, these two acidified, right? And then to decide, do you want the left hand side, which means H2O2 undergoing reduction, or the left hand side H2O2 undergoing reduction, or the right hand side H2O2 undergoing oxidation. So what we want is actually the H2O2 being oxidized on the right hand side. So this is the value to use. So this value you have to substitute it in, and you realize again this is a positive value. We're expecting the reaction is spontaneous in this sense. Okay, I hope you didn't pick the wrong value and end up with the wrong answer. If you've done so anyway, this is a learning point, right? Trying to pick out the correct equation in the data booklet can be a bit tricky. You must understand quite clearly on the left or the right hand side to pick that out. Alright, so the overall equation as required as well. This case has a 5 electron and 2 electron factor. You need to multiply by 2 and 5. Okay, this will end up with this as the overall equation. Okay, the H plus 16, while on the right is 10. So that will give you a total of 6 on the left hand side. Okay, the rest, not much of an issue. H2O2 as it is, O2 as it is. Alright. Okay, we have done the bulk of the uses of standard electrode potential earlier, especially the two parts in the learning outcome, which is to calculate the standard cell potential and also to use the standard cell potential to predict whether a reaction, a redox reaction, is spontaneous or not. Right? So now we're going to look at 3 more uses in a very quick manner. One is to predict stability of the metallic ion in different oxidation state. So in this case, if we want iron 2 plus rather than iron 3 plus, you realize that there are a couple of equations we can look at from the data booklet as well. One is in acidic medium, one in the alkaline medium. Okay, this is the case for a few of the transition metal ions that you can pick up from the data booklet. We will learn again more of this later on. But looking at this example, you realize that the fall reaction is more likely to occur for the acidic medium. So if we want iron 3 plus to be oxidized to iron 2 plus, the acidic medium is the one that would most likely to cause it to occur, right? So with that, the more positive one, indeed, if we want iron 2 plus, it will be more stable in the acidic medium. Okay, it's not just acidic and alkaline. There's also many different what we call ligands, which you will also learn at a later stage, and we can use the data booklet standard electrode potential to help us to do such predictions. Okay, the next idea, alright. So the next idea that's involved is looking at metal extraction. Okay, you've done a little bit of that at O level, but we'll go through a bit quickly here as well. Okay, for those who have done pure chem, you understand in terms of reactive metal, high electrochemical series can only be obtained by electrolysis of the molten compound. Okay, electrolysis is used because these oxides cannot be reduced by carbon, and aluminum is extracted by electrolysis as such. Okay, so I will not go through in the depth of this, but what we can understand is that for those electrode potential, they are very much more negative, they are very reactive metal. It's very difficult to extract them by chemical reaction. You probably need electrolysis for this to occur. Okay, next and the final one is preventing of rusting. Okay, so for example, in this case, where we have a steel nail in the water, okay, already air that's involved, and another steel nail, but in this case it could be wrapped around by a zinc sheet in that sense. Okay, so using a zinc sheet is sacrificial. It will be the zinc that's undergoing redox a bit slowly though, rather than the iron itself. Okay, so this prevents iron from rusting. We can again use the electrode potential values to compare. The case is more negative, so anything below iron such as zinc, even magnesium, but magnesium may react with acidic water quite a bit, so it depends. But zinc and magnesium are two good examples in that sense. Okay, more negative, you want to join the metal together, it will prevent or slow down the oxidation of iron, okay, which is rusting itself. Alright, so the protection of this is considered galvanizing. So a lot of galvanized roof, the older metal roof are done in this way. The electrode potential value are shown as such. So you go through sacrificial rather than the iron itself that's being oxidized. So more negative, it will be a sacrificial corrosion or protection in that sense. Okay, now we want to consider the limitation of the standard electrode potentials. Specifically in the syllabus is the limitation of standard cell potential for predicting spontaneity of a reaction, right? So while firstly we need to consider that this electrode potential value relates to spontaneous, okay, relates to thermodynamic, whether is it feasible or not energetically in that sense. It relates of course to delta G, like a positive E0 value will give you a negative delta G. This one will come to it later on. At the same time, equilibrium constant. So these three topics or three sets of ideas relate to each other, they are correlated, and it goes on to thermodynamics, whether it's spontaneous or not. But it does not tell us the rate of reaction, right? The rate of reaction doesn't relate to delta G or Kc or E0 directly. So in this case, for this example, we have stated that actually we all know that dichromate oxidizes methanol, right? Dichromate oxidizes methanol, the E0 value is positive, it shows us that's the case, it's spontaneous, but there's no reaction and it requires heating in fact, right? Because it's actually very slow, and when we're very slow, we are talking about high activation energy, correct? So the activation energy is high, the rate constant, the small k is probably very small, right? This is a low value. And now you need to increase the temperature so to increase the rate. Okay, this is another aspect of a reaction to consider. So every reaction, there's two aspects. One of it is thermodynamics, which we can use delta G. We can use a large equilibrium constant to say that, oh, it's spontaneous. We can use a very positive cell potential value to show that, oh, it is indeed spontaneous, but it does not mean the reaction would definitely occur readily at room temperature. There's also a kinetics part to be considered. Okay, so that's one limitation. The second limitation is due to the term here as standard, right? Because of standard, there's a certain 1 bar that we have given to it, a certain temperature of 298 Kelvin, a 1 mole per dm cube that we have given these values. Okay, but in non-standard condition, like in this example, if we had used a concentrated HCl, although a standard value will show that it's less than 0, it's not spontaneous, okay, it's negative, right? But if we use a concentrated HCl, it will react with MnO2. Okay, it's well known, we have shown these reactions before because of a non-standard condition. Okay, so how much would it change in that sense? As a ballpark figure, usually we are looking at maybe around 0.3 volts. Okay, that might be still affected, possibly affected. Okay, so that's a ballpark figure. There's no need for you to know an exact figure to it, just have to depend on the question in that sense. Okay, so if we go on, now let's look at this work example in the next page, right? If we do a simple calculation here, you expect this to be positive 0.43 volt under standard condition. Okay, so this is standard condition. If I put a standard value here, this will be what you expect. It will be a spontaneous reaction. And now we want to see if we change the concentration, how would it affect this reaction? So as earlier stated in section 2, okay, the discussion of how it would change, how the values would change, the electrode potential values, depends on the position of equilibrium shifting. So firstly, if I increase the concentration of iron 3+, so this is a bit more straightforward, then certainly POE will shift to the right, and then it will favor the reduction equation. So therefore, this value will be more positive, right? So maybe now it becomes plus 0. Maybe 84 volt. Okay, more positive. So now the E cell itself would also become more positive, okay, as a value of maybe plus 0.50 volt. So part A is an easier explanation to look at, more straightforward. Now let's look at part B. Part B, firstly, do not flip this equation, okay. Just treat it as it is because we are going to use the value as it is. So we are not going to reverse and talk about POE shift. We're going to keep it as a reduction forward reaction and discuss about POE shift. So in this case, POE will shift to the left, right? Because you decrease the concentration of copper 2+, POE shift to the left. The Chatterley's principle, right, counteract the change. So now this favors the oxidation reaction, copper to copper 2+. This value will be more negative. So let's say now we change the value to plus 0.27 volt. Okay, so now that it is more negative, what happened here is that the E cell will become more positive, right? If we sub the value in, which we have, let's say standard 0.77 minus 0.27 now, it's going to give you a positive 0.50 volt, which is greater than the standard that we calculated, or more positive than the standard that we calculated earlier, right? So these are some values just to give you a sense of the discussion. Okay, so the main thing is, if it's a standard condition, not too bad, but once we change concentration or pressure, there's some limitation in predicting the spontaneity here, as well as the earlier part, it gives us spontaneous reaction or not, but it doesn't tell us about the rate of reaction. Alright. We mentioned quite a bit about cell potential and how it relates to whether a reaction is spontaneous or not, and it's quite logical if it's positive, right? A positive value will give you a spontaneous reaction. There is also a relationship between delta G and a spontaneous reaction. We learned that earlier last year. So now we are trying to find a relationship, a mathematical relationship between these two entities in that sense. Okay, so in fact, the energy generated from electrochemical cell, which is the free energy in that sense, the Gibbs free energy delta G, can be accounted for by the cell potential in voltage and the amount of electric charge that's passed through. So those of us who do physics would have a greater sense of this idea about energy is where the amount of electric charge multiplied by cell potential or potential difference. But not to worry, the main thing we need to be very clear of is this equation. As a chemistry student or H2 chemistry, you need to remember this equation. You need to be able to apply this equation. So to apply this equation, you have to take note of the negative in front here, negative NFE, right? So with the negative value, negative here, it will help us to convert a positive value to a negative value to have the inverse relationship with delta G. So make sure you have the negative sign there. And N is the number of moles of electron that's transferred. Okay, so earlier when we did E0 cell or standard cell potential, we say we ignore how much electron is transferred. Now we need to account for it. F is a Faraday's constant. It's in this unit. You use this more in part 2 of electrochemistry later on. So for now, 96500, we just need this. It's also in the data booklet as well. So we need to sub this inside. Okay, this is the charge for, this is the unit of charge for 1 mole of electron actually. Alright. So we firstly have to understand, okay, this is work example 7, that is 2 electron transferred here. So this is not a spontaneous reaction indeed, negative value here. We sub the values in. So the 2 you sub in, 96500, negative 1.19. And at this stage, you're actually looking at the units of joules per mole. Okay, so this is actually just in joules per mole. And if we want it to be in the usual unit of kilojoules per mole, we have to divide by 1000, right? So this is the important part here, and also put down as a note beside the main equation. Okay, so do take note. And then we can get the correct value. Again, the positive sign must be there. Okay, if it's positive sign, you have to put it down for delta G, delta H, delta S, and E naught. Right? So it is consistent, obviously, because of the negative that we have put in. It's a positive value in this sense. Okay, let us look at lecture practice 6. Okay, I give you a bit of time to try and do it. I'll carry on in about 5 seconds. Do pause the video if you need to. Okay, lecture practice 6 already written for you. To take note that there's 5 electron transfer here. So to substitute the value in, right, we will just get the 96500. The cell potential is also calculated for you. So you just have to substitute in. Again, remember to divide by 1000 so they can get the correct answer. Okay, the answer is also provided, so I do hope that you have attempted this. Okay, this is not a spontaneous reaction. This is a spontaneous reaction given by positive cell potential value and negative delta G. Let us look at work example 8 to finish this up as well. So for work example 8, right, you have to start off all the way by calculating. So you have to find the relevant half equation. You have to calculate the cell potential value, standard cell potential value, and then using the standard cell potential, you can substitute it in, and this is 2 electron transfer, okay, and divide by 1000, so to get the negative 147 kilojoules per mole. So let's give it a try for lecture practice 7. The numerical answers are already given, but do take the effort to go find the correct values. Okay, importantly, be able to pick this out from the data booklet, right? Okay, do pause the video if you need to. Okay, I'll carry on. So having these correct values and looking at this, the oxidation part is dichromate getting reduced, right? So you have 1.33 minus 0.77. Okay, it gives you a positive cell potential value. This is a spontaneous reaction, it seems. The number of electron transfer is a little bit trickier. So this entire balance equation reflects 6 electron transfer. I hope you got that. And then by substituting it in, you will be able to divide by 1000 to find the negative 324 kilojoules per mole. So there are plenty of examples of practices for this, and you realize that this entire first part, we do need to calculate and pick the correct value quite well here, and also further on to calculate delta G if required.
But any battery has a finite supply of metal, and once most of it has oxidized, the battery dies. So rechargeable batteries give us a temporary solution to this problem by making the oxidation reduction process reversible. Electrons can flow back in the opposite direction with the application of electricity. Plugging in a charger draws the electricity from a wall outlet that drives the reaction to regenerate the metal, making more electrons available for oxidation the next time you need them. But even rechargeable batteries don't last forever. Over time, the repetition of this process causes imperfections and irregularities in the metal's surface that prevent it from oxidizing properly. The electrons are no longer available to flow through a circuit, and the battery dies. Some everyday rechargeable batteries will die after only hundreds of discharge-recharge cycles, while newer advanced batteries can survive and function for thousands. Batteries of the future may be light, thin sheets that operate on the principles of quantum physics and last for hundreds of thousands of charge cycles. But until scientists find a way to take advantage of motion to recharge your cell battery, like cars do, or fit solar panels somewhere on your device, plugging your charger into the wall, rather than expending one battery to charge another, is your best bet to forestall that fatal bleep.
we have come to the last part of part 1 of electrochemistry. So now we are looking at some practical application of electrochemical cells. There is a whole listing of what's a primary cell, secondary cell, and a battery. You don't really need to recall this at all. So I'll leave it as that. Where it says non-rechargeable and rechargeable. As well as on this page, there's a TED video that you have watched earlier in the first SDR lesson, and I've rehashed it in this SDR lesson to watch it again, so to better understand the context. Nonetheless, there's one very important learning outcome that we all need to get to, is to state. So this is a recall learning outcome. Possible advantages of developing other types of cell, such as the fewer cell, which is important. We'll come to that. And in terms of smaller size, lower mass, and higher voltage. So having said all that, these are interesting things to look at. You will see the fuel cell as well. Many batteries for us to go through as examples, but they are examples. They are applied from the electrochemical cells that we have done earlier, all the way, earlier on, where we look at galvanic cells, right? At 4 and 5, the calculation as well. So these are applied in that context, section 4 and section 5. So not to worry here, we are going to go through them at a rather speedy pace because the main thing we're looking at is smaller size, lower mass, higher voltage. These are advantages. So the main thing we are focusing on will also be advantages and disadvantages of the various batteries. Alright, so firstly, galvanic cells and batteries provide a very useful and economic way of providing electricity in that sense, very portable. So there's trend in improving, trying to get to smaller size, lower mass, higher voltage. Something different here that is not in the learning outcome, also at a lower cost and longer shelf life. So basically, we want to be able to keep the battery or the energy stored in the battery for as long as possible. So there's development of improved batteries, and we are moving away from just simple cells to fewer cells, and fewer cells have its advantage. And we are going towards electric vehicles as well. So the lithium ion cells as such, or solid state batteries, also have their various advantages. But historically, we go off starting off the zinc carbon dry cell, where we need a certain electrolyte that's involved. There's a paste here, and the oxidation occurs at the anode. So again, I'll go through this quite quickly. This is more of an applied concept, not for you to recall. So we have that in our normal battery that we have, that we tend to buy, and once we finish it, we throw away the alkaline batteries. A similar kind of setup. So this are the various reactions that's happening: the reduction, the oxidation. You increase surface area of the cathode in that sense, so that you have a larger current flow, right? The EMF is 1.5 volts, so your AA battery, AAA battery, I think you're familiar with that. It is cheap and portable. It's a reliable voltage, but it's not a perfect shelf life kind of scenario, so that's the disadvantage, right? With the zinc casing, it does disintegrate over time, and the paste also would ooze out of the outer shell. That's where we commonly, or we have experienced before, like battery leaking. Correct? If you put the battery, leave it there for too long, it might leak in that sense. The voltage is not very high, it's only at 1.5 volt. It definitely cannot be recharged. It's considered primary cell. As an alternative, and what we are using more day to day, it will be the alkaline cell, dry cell in that sense, where we try not to use a paste, but some potassium hydroxide instead of the ammonium chloride scenario, and zinc carbon. So in this case, because of the hydroxides, right, you can imagine that the corrosion is actually much slower. But it's completely discharged. It also cannot be reversed or recharged. So we go on to the next stage of developing rechargeable batteries or rechargeable cells. The next kind of cells that we want to look at is a lead acid accumulator. These are found inside car batteries still quite often. Basically, you would find them in vehicles these days as car battery. The one that when you want to crank your engine to start up, that's where you use the energy from. There's a platinum plate here coated with the platinum oxide cathode, while the other one is just a pure platinum plate as the anode. The electrolyte is the sulfuric acid. These are the reaction that's happening, and With that, the theoretical value of the EMF is actually 1.6 volt. Okay, but the actual EMF is 2 volt and not 1.6, and we have a quick discussion of why is that so. And in fact, 2 volts times 6 give you a 12 volt battery in your car. That's written in the notes as 12 volts. So times 6 is because the battery is connected in a certain way. The cells are connected in a certain way. Again, that's more of that physics concept. But I think as a general science idea, we can understand that when it's connected, right, in a series manner, your voltage actually adds up together. Okay, connected in series. All right. So it has to do with this lead 2 plus here we're going to talk about, and lead sulfate actually gives you a solid. So that decreases the lead 2 plus concentration quite a bit. That allows us to shift the PoE to the right significantly, about 0.4 volts in that sense, giving us a 2 volts outcome. At the same time, if you look at the anode reaction, right, and the cathode reaction, they are both affected in the same way, that when the lead concentration decrease, your PoE shift to the right. So it's affected both ways. So that gives you a more positive value and a more negative value here, and that changes it to much greater than 1.6 volt. Again, this is more of an application context, not as a recall. I emphasize it's not as a recall, but do understand that it can be asked as an application context, and you should be able to pick this out. How does the potential value changes in that sense, right? Concentration has changed. So what affect concentration? Because precipitate is formed, and both cases, right, you move it. Okay, maybe it goes up to be 1.67 volt now, and it goes down to be negative 0.33. So that allows you to get up to a 2 volt scenario. Okay, so do consider that. So again, what I'm stating here is that it gets more positive to maybe plus 1.67 volt, and more negative to become negative 0.33 volts, right? So when these two adds up together, or rather subtracted, okay, it will give you a 2 volt scenario. So again, an application context. Okay, so that film of lead sulfate is indeed observed. The concentration and the relative density of the H2SO4 reduces. Okay, indicate the state of the charge. So when it's fully charged, your sulfuric acid has a relative density of 1.275 volt, and when it's recharged, you can apply an external current through the electrode reaction. So this actually do occur in the car, right? You have a lead acid accumulator in the car when you're driving using the combustion engine or electrical engine, depending on the kind of car you have. It will recharge the cell. Okay, so this is a rechargeable cell context. There's a case of discharging and charging. Okay, so far we have been looking at discharging. You learn more about charging in the next part of electrochemistry. Okay, so the advantage is certainly that there's a heavy initial current to start the car, but the disadvantage is very large and very heavy. Okay, it produces lower power for its mass. Other things you can think about is of course lead acid accumulator. The lead itself is quite toxic. You do need to manage it quite well, right? So these are some disadvantages to consider. Okay, of course the day-to-day cell now that we have that's rechargeable in your handphone tends to be lithium-ion battery. That's another context separately. We can put up a video for you to consider that, again, as application, not as a recall. It's never as a recall context. Okay. Now, fuel cell though, fuel cell is quite important here. I do state so because the learning outcome states specifically other types of cells development. Example, H2 and O2 fuel cell, right? So these are improved batteries. These are not just improved batteries, these are different type of cells altogether. Okay, so for fuel cells, you can continuously replace the reactants as they are consumed. So there are many kind of fuel cells that we can consider. It could be, the easiest is oxygen in the air. So that's one good example. But at the other side, we can have hydrogen, hydrocarbons, alcohols. So these are all possible scenarios, and A-level have set these scenarios before, okay, as application. And certainly in prelim, we do see them often. So the example that we want to focus on is hydrogen-oxygen fuel cell. as stated specifically in the learning outcome, but it can be applied throughout. Okay, so these cases, the fuels itself are clearly requiring an inert electrode. Okay, it is not the case where there's a metal electrode that's involved in the half equation. So one side, the easiest is oxygen. The other side that needs to be oxidized, okay, could be hydrogen, could be ethanol, for example, ethanol fuel cell, right? It could be methane fuel cell, right? So all these are possible. Okay, so in this example, at the anode, there's oxidation that occur, cathode reduction. So oxygen is a very often used at the cathode. It's easily available in the air, so therefore it's very often used at the cathode for fuel cells. Okay, but your choice at the anode can be varied. So in this case, looking at the values that you can sub in, you calculate, you'll be 1.23 volt. The example we have given here is an alkaline example. So this equation that you picked from the data booklet has to be the OH minus 1 as well for the H2 gas. So this is a bit different. Okay, so do take note of it. So the advantages, they are considered pollution free. Okay, fantastic in that sense. High power to mass ratio, highly efficient, right? You can have them in a very, very small context. See a micro fuel cell that you have in fuel cell bike. So that satisfies the idea of smaller size, lower mass. That's one of the learning outcome. All right. It's pollution free, as high power to mass ratio, highly efficient, right? Okay, expensive though because of the catalyst that's involved, and it can be easily poisoned, and the high temperature may be required for the reaction as well. So I'll leave it as that to end off at this topic, and there'll be a bit more video for you to look at if you're interested, okay, on lithium batteries as well as hydrogen oxygen fuel cell. All right, thank you.